number 8. Number 8. I got it circled there. Now, based on table I, which equation represents the conservation of mass and energy? All right, my friends in chemistry, you should know that every time a reaction is written with its energy, you should know that mass, energy, and charge are always balanced. Okay, I know the charge part isn't part of this question, but just be aware that all those three things are involved. Now, in this question, they want to know which one is the conservation of mass and energy being followed. So we should understand that the conservation of mass part is balancing. Do we have the same number and same type of atoms on both sides of an equation? So anytime you hear of conservation of mass, you should think as, is the reaction balanced? Right? You spent time making sure that you have the same number and same type. So if you look at choice 1 and 2, you can see on the reactant side, which is to the left of the arrow, I only have 2 oxygens, right? So we have two oxygens there, right? So 2 oxygens. And here we've got 2 oxygens, okay? But we have 2 on the CO2, but we also have an oxygen here on the water. So that's 3 oxygens on one side. So on the product side, which is to the right of the arrow, we have 1 more oxygen than the reactant side. So we are not following the conservation of mass. This is not balanced. We're actually creating an oxygen out of thin air. So we can eliminate this. I don't care about the energy because they said and. So who else is balanced correctly? All right. So, or incorrectly to cancel out in this case. I'm going to eliminate the questions, okay, that I know are incorrect because they're not balancing correctly. Look at number 2. We've got 2 oxygens on the reactant side to the left of the arrow. Okay, you've got to know that to the left of the arrow is your reactant side. On your product side, to the right of the arrow, let's count oxygens. We have 2 on the reactant side. We just got those here. And notice we have 2 here plus an oxygen here. Same deal. We have more oxygens being produced than we started with. You can't do that. Okay? Every single atom that we have on the reactant side must be the same number and same type on the product side. So we're creating an oxygen out of thin air. That's not correctly balanced. All right. Now if you check out 3 and 4, hey, we have 2 times 2, okay, 4 oxygens to the left of the arrow. And then we have 2 here in the CO2, and then we have, don't forget the 2 in front, there's 2 times 1 there. So there's a total of what? Okay, there's a total of 4 electrons on this product side. So that makes sense. There's 4 on this side. Okay, oops, I got the wrong tool here. I've got 4 on this side and the 2 here plus the 2 that I got from there. So that's balanced. The oxygens are balanced. And of course, there's 1 carbon, there's 1 carbon, there's 4 H's, and there's 4 H's. So if you notice, everything's balanced. And so is choice 4. The same coefficient 2 there and a 2 on the water. So you can see that choice 3 and 4, they have the same coefficients. Those are the things that we call mole ratios that we help to balance reactions. So they're balanced the same. The only difference now is the energy. Who is showing conservation of energy? And all this means for you guys is that the energy is written correctly in the reaction. Notice we have the energy written in front of the arrow. That'd be endothermic. You need that to go forward, right? You're in front of the arrow. And then we have the energy written after the arrow. Okay, right here's the arrow. So this would be exothermic, right? You need to know that energy written on the product side is exothermic. And then the energy written over here in front of the arrow would represent an endothermic. So that's where you're going to need what? Table I. Okay, and by the way, table I has balanced reactions too, so you could have gone there and seen which of these reactions is exactly written as in table I. But what we should know is that these reactions 1, 2, 3, and 4 is combustion. It's burning. okay? We use oxygen with a carbon-based fuel, and we make CO2 and water and a lot of energy. Combustion is exothermic. Now, if you didn't know that, go to table I and let's go there to find this exact equation written balanced and with the right energy. So let's go to table I. I like table I. So here we are with table I. Again, I like this table, but more importantly, the reaction we're looking at is right here. And if we look even closer, okay, we can see that we've got two O2s and two H2s. So this reaction is balanced as we had in choices 3 and 4. The hardest part, I guess, is that you've got a negative value here for delta H. You should know that delta H is the heat of reaction. It's the amount of energy that changes. That's why that symbol there, that delta symbol, is the change of heat or energy. Is it going into the reaction or out? Because it's negative, it's telling you that it's going out. You're losing money, you're losing heat. If you got negative money or negative something, that means that's how much you lost. And losing energy is exothermic. So the energy is always written on the product side, okay, in exothermic reactions. So you had to know that delta H was negative there. But do you really? Because if we scroll down, okay, they tell you that if something is what? Exothermic, there's a minus sign. You just had to know that exothermic means the energy is going to be after the arrow there. Okay, so a lot of hints there for that question. Any case, it's written just as this is, and the energy is, delta H is negative. They tell you it's exothermic. You just had to know, again, energy on the product side is exothermic. So that's why choice 4 is the answer. Let's go back to our test. So choice 4 is your answer. And again, you have the coefficients in front of the O2 and the H2 to have the balanced reaction, conservation of mass. Energy written in the what? Products area, which screams to you exothermic, as it was given in table I. So number 8 is 4. On to number 9. Number 9, at STP, which property can be used to differentiate? That's a very advanced word, but basically differ is in that word. So how does one, how can you tell one from the other? In a 10-gram sample of sodium chloride, hey, that's a compound, 2 capital letters, 2 different elements, from a 10-gram sample of sodium nitrate, another compound. This one is a tertiary compound. It's got 3 different capitals, 3 different elements, but those are compounds. So how can we tell that we have one compound from the other? Well, as I have stated previously, if the formula is different, then the properties, chemical and physical, will be different. Okay, these will have different sets of property, and that's what compounds are. They're different from each other because of that different arrangement. But can we tell one compound from the other by just the mass alone? If I have 10 grams of one and 1 gram of the other? No. Any compound can have any mass, so that makes no sense. And any compound can have what? Any temperature. You can't say, well, NaCl is always going to be warmer than NaNO3. That's kind of silly too. All things can have any temperature depending upon how much energy you give it. Okay. Solubility. Well, that is a property that is unique, okay, to each compound. And solubility is the ability of the water, the solvent, to dissolve a certain amount of each of these compounds. If one can be dissolved in a greater amount, can actually dissolve in a greater amount with the same amount of water in the same temperature, it is more soluble. Okay, so that is definitely going to be your answer. Solubility is a property. It's an intensive physical property, and you don't need those fancy words, but intensive physical property are properties that depend upon the identity, like density. If you had the density of these samples, you could identify them. If you knew their melting points and boiling points and you actually melted them and took the temperature, you can identify them. Okay, going back to the choices, phase at STP, well, these are ionic compounds because they're what? Metals and then non-metals, or in this case, metal and non-metal. So these guys are all solids, by the way. as all ionic compounds are at STP. So they're both solids, and you can't being solid isn't enough to say one's different because they both are. So 3 is the answer, solubility. By the way, you have a table, a reference table, table G, that shows you solubility curves of how well these compounds are. I'm going to show you anyway, whether you like it or not, onto table G. So here is table G in all of its glory. We can see sodium nitrate has this curve, okay, has this curve right here as I write over it. And then we have, okay, sodium chloride, NaCl, has this curve. All right, and you could see at these grams here, sodium nitrate at every single temperature in 100 grams of water is more soluble, right? If I compare the solubility, let's say at 100 degrees Celsius, I can see that a saturated solution of NaCl is about 40. And if I talk about sodium nitrate, well, it's going to be greater than that because that line keeps going. Not a great example to get off this curve, but we can see that sodium nitrate would have a heck of a higher amount of solubility. You can see that 150, this is 160, something around 170 there. Okay, so clearly sodium nitrate with a higher curve means that there are what? More grams of it can dissolve in the same amount of water at similar temperatures. Okay, so be aware that you have solubility curves, and it's a physical property. When we dissolve these things in water, they're not chemically changing. All right, they're changing into an aqueous phase. So again, number 3 is your answer there for number 9. On to number 10. Number 10, what is the number of electrons shared between the two atoms in an O2 molecule? Well, oxygen is a nonmetal, and when it bonds to another nonmetal, even itself, electrons are shared. These are covalent. Co means they're sharing, cohabitating, right? Electrons. And the reasoning, of course, is they both have high attraction for electrons. But if we draw the Lewis dot structure for oxygen, we're going to draw an O, and we're going to put down all of its valence electrons, right? So we're going to go 1, 2, 3, 4, 5, and 6, and we'll draw another oxygen and draw its valence electrons. 1, 2, 3, 4, 5, 6. And then you say, well, how do I know there's 6? If you look up oxygen in the reference table, you'll see 16 for its mass. You'll see 8 for its atomic number, but below that, you're going to see 2-6. The outermost electrons that are unstable, okay, are your valence. So sometimes I'll just ask for electron dots diagram for an element, and the dots equal the valence electrons. We don't care about these electrons in the inner shell. Don't forget, this means 2 electrons in a shell that's closest to the nucleus, and these are electrons that are farther away. They feel the nucleus less. These are the electrons that have a high enough energy to be involved in bonding. Okay, any case, so what we do is we always start with a bond, and then we kind of check as you go there. There's a couple of different ways to do this. So what I'm going to do is I'm going to remove this electron, and then I'm going to put that right here. Okay, maybe. Okay, so I'm going to put that right there. And then I'm going to remove another electron. I'll take this one, and I'll, okay, put that right here. Now, I'm going to evaluate what I have so far. By sharing, this oxygen feels like it has 1, 2, 3, 4, 5, 6, 7. And by sharing, this one feels like it has 1, 2, 3, 4, 5, 6, 7. Right? So I can see that this is not going to work because we know 8 electrons fills the octet. And the octet means we want to fill this shell here till it gets to 8. So each oxygen wants to share, guess what? 2 electrons. So we got to keep going here. We've got to add a second bond. One bond is a pair. So I'm going to take that one away, and then I'm going to put that one here. Oh, let's keep it the same color. And then I'm going to take this one away, and I'm going to put that one right here. And now you can see this oxygen, by sharing a pair, feels like it has 8, and this one, by sharing, feels like it has 8, and both have reached what we call the octet. Now we can also rewrite this as an O double bonding to another O. Okay, my O here is ugly, but we have 2 lone pairs left over. And this would be the same thing if they were to ask you to draw a Lewis dot structure of that. Remember, the lone pairs must be shown. So this one dash here represents 2 pairs. The other dash here represents the other pair. So back to the question, how many electrons are shared between the 2 atoms? Well, they're talking about the electrons in a bond. And therefore, because there are 2 bonds, there are 4 electrons being shared, or a total of 4. Now be careful with this question, because sometimes they'll say number of electron pairs. They could have said that. They didn't. And the answer would be 2 there, because a pair is a bond. Okay, so just be careful of that question there. Okay, so obviously the answer is total of 4 electrons shared. 10 is 4. On to number 11. Number 11. Which change in both charge and radius occur when an atom loses an electron? Okay, so 2 parts to this. Losing an electron, and of course we know electrons are negatively charged, right? If you go to table O, we'll see that the beta particle is given a 0 mass, an E for the electron, okay? A 0 mass, an E for an electron, and a charge of -1. I can get that right from table O. The bottom number is the charge. And they give it a 0 mass because it's 2,000 times lighter than the proton or neutron, so it's insignificant to the mass of a atom. Okay, so if you lose a negative, we should know that the resulting ion should be positive. You lose negativity in your life, you become a more positive person. And we've seen this in redox, my friends. If we take a metal like sodium, and if it loses an electron, 1e negative, remember we wrote that, it's going to become Na plus. And how do I know? Because your teacher said, hey, the charge on one side has to equal the charge on another. Atoms that hang out by themselves, okay, have 0 what? Charges. And this whole side is also 0 because it's a +1 and a -1. This is called conservation of charge. All reactions have it. Redox reactions, it's really in the forefront. Electrons are being passed around. By the way, this is called oxidation. Don't have to know this for this question, but you should know this for the entire test. Everything kind of fits together. So losing negatives makes you positive. So you should know that choice 1 and 2 should be gotten rid of. Easy for me to say. So no negative ions are formed. Negative ions are formed is when you gain a negative. We're losing it. And by the way, for those that were going over another question with me, anything to the right of the arrow is something that is released or lost or produced. So losing electrons is oxidation. Now the question is, what happens to the size? People mess this up all the time. So if I have an atom, and this is its atomic radius, and if it loses an electron, it's going to become an ion. In this case, it's going to be a negative ion. The question is, does it get bigger or smaller? Okay, and I probably should have started this a little better. So let me redraw the atom. Oh, Christmas in July. So let me just go back on this a little bit. So let me write my atom, all right, in a way that I can either go bigger or smaller with it. Okay, so let me go, here's my atom, and then we're going to go to an ion. In this case, it's a positive ion. You may have called it cations. Now, does it get bigger or smaller? Okay, well, the best way to remember this, okay, I'm going to give you how I would teach it, and then I would give you the best way to remember it. If you lose negativity, don't forget we have what? We have positives in the nucleus, and we have electrons outside the nucleus. We know that if you have an atom, okay, I say atom, you say neutral, atom, neutral, electrons always equal protons. So in the case of sodium, since I started with sodium, sodium's atomic number 11, which means it has 11 protons. Okay, so it's +11 in the nucleus. And it also has 11 electrons. Now, they're not all in one spot, but I'll just do a negative 11 for all the electrons that are outside the nucleus. And so that negative and positive 11, negative 11 gives you a total of 0. That's why atoms or standalone elements are always written with 0. You should see the connections between the units here, okay? So if it becomes positive ion, because you lose a negative, oh my gosh, you can see that the protons are going to outnumber the electrons. So if I lose an electron, well, this now is going to be negative 10 outside the nucleus. Okay, and you could see that a positive 11 is now bigger, so the greater positive is going to pull the electrons in closer and it gets smaller. A positive ion is always smaller than its atoms or its atomic radius because the protons outnumber the outside electrons and pull them in. If you don't like this, okay, as a lot of students don't, here's the best way to remember this. I am losing electrons, okay? Think about losing electrons like losing weight. When you lose weight, you get what? Smaller! So we're losing electrons, so the resulting ion is smaller than its atom. And they use this terminology, the ionic radius, the charge of the ion, is smaller than its atomic radius. I'm sorry, the ionic radius, the size of the charged atom or ion, is smaller than the atomic radius, okay, the size of the atom that's neutral. By the way, if you gain electrons, let's look at chlorine, and it gains an electron, that'd be 1e negative, so we call reduction. So if you go from a 0 to a negative, because you're gaining negatives, we get bigger because you're gaining electrons or you're gaining weight. So think about electrons gained and lost like weight. You lose electrons, you lose weight, you get smaller. You gain electrons, you gain weight, you get bigger. Okay, so in any case, back to reality here. Up there goes gravity, and I probably have to owe some money to someone for that. But a positive ion is formed with a smaller radius than the atom, okay, because you lost electrons, you lost weight. Number 11 is 3. On to number 12. On to number 12. Which statement describes what occurs when two iodine atoms react to produce an iodine molecule? So atoms are coming together to produce a molecule. So what does that look like? So we have an iodine atom plus another iodine atom come together. I guess it's more money, I hope, people. And they make an iodine atom that's bonded to another iodine atom. Okay. Forgive me for the bad art. But we did what? A bond was formed, right? These were free atoms and they were bonded. So two I's became I2. It's a difference. Two of the individual iodine atoms, now they're bonded into one particle. That's an I2. So a bond was formed. A chemical bond. So that needs to be understood. So bond forms. That's why we can get rid of 3 and 4. Bond is not breaking. We're putting atoms together into a diatomic molecule. Okay, now the question is about the energy. All right, what's happening to the energy? Okay, we've been through this plenty of times for my class, but people forget it. Why do atoms bond? Why do chemicals do the things they do? Why does anything do the things they do? Things in nature are trying to get to lower energy. This is so gosh darn important. So the reason why iodine and iodine can form a bond is because this state right here is lower energy or more stable than what? The original state. Things in nature go from high to low. So you should know stable means low energy. And therefore atoms together that can react must be what? High energy. So the reason why bonds are formed is to get to a low energy position. A rock on top of the hill, my friends in chemistry, is going to eventually move to the bottom. It never goes the other way, okay? You know, birds are going to land without putting any energy into. Spontaneously, birds land. But when birds want to fly, they have to what? Use their muscles and energy to fight gravity to fly. These are things you should understand. So anytime a bond is formed, you've got to understand that energy is always released. So therefore, 2 is the answer. Another way to remember this is that after I'm done with this video, we're going to meet together and go into town and break stuff. No, of course we're not. But if we want to go break stuff, okay, we need energy, all right? You need energy to break something, and therefore energy is released when you form it, if you want to think opposite. But think about it. Why do atoms bond? They want to get to a low energy position. And we kind of explained this throughout the course. I don't care who your teacher is. Hey, why does, okay, hydrogen want to bond with oxygen? Well, because oxygen has a single electron that it can share with hydrogen. And why does another oxygen bond with, remember, oxygen has 6 valence electrons, and one bonds with one hydrogen and one bonds to another hydrogen. So why does that happen? Because oxygen wants to feel like it has 8 electrons. It wants to fill its outermost shell. And why do we care about that? Because when you fill the octet, wait for it, a filled shell is stable. Hey, let's go look at the iodine. Iodine has 7 valence electrons. How do I know? Its last number given to you on the bottom of the iodine in your periodic table is 7. It's the outermost. So they both have 7 outermost electrons. You put another iodine together. I'm changing colors, hope you can handle it. I'm going to put its 7 valence electrons, and you can see it's a great match. When they come together, they're both going to feel like they have their what? Octet, which, my friends, is stable. When atoms have that filled octet, they're good. They're not going to react anymore. They're lowest energy. Hey, do we know atoms who don't react because they're already at the octet? Oh my gosh, we do. Those are the noble gases. Okay? All the noble gases, group 18, have those filled either PRS orbitals. More importantly, they have, generally speaking, have that 8. We'll keep it at that. Okay? And that getting that octet is a stable scenario. All right? So that's why all of this fits together. If you don't see this big picture coming together and trying to memorize little facts, this is how this works. So number 12 is 2 on to 13. Number 13.